Okay, hello everyone. This is lesson 1.5 on acceleration. And so usually when we start introducing something like this, the first key question is, well, what is, in this case, acceleration? Acceleration is simply a change in velocity. So change in velocity. Now, a change in velocity can include either the magnitude, which is the speed, or direction. Right? If something is moving at, let's say, 2 meters per second this way, and then a little bit while later it is moving at 5 meters per second this way, to the right, it is a change in velocity that is happening over a period of time. Right? But let's say if an object is moving 2 meters per second to the right, and then a little while later it is moving 2 meters per second to the left, that also is a change in velocity. Now, it's not a change in magnitude, the overall speed, but the direction has changed, which means something has happened to cause that change. And so either magnitude or direction for the change in velocity. Now, this does happen over time, and so the main formula you're going to be looking at is A is equal to delta V over T. And we put the arrows on top because acceleration is a vector. It does have both magnitude and direction as well, because the change in velocity could be either the magnitude or the direction. In this case here, we see a change in velocity. In case number 1, we see a change in velocity of 3 meters per second to the right. In the second scenario here, we see a change in velocity of a total of 4 meters per second to the left. Right, to the left, correct, to the left of your screen, because you were going 2 meters per second one way, and you are now heading 2 meters per second to the other way. So one key difference between what's a V is equal to delta T d over t question and an acceleration question, well, this formula represents what we call uniform motion, right? Which means that we have a constant velocity in this case. If you have an acceleration, you're seeing a change in velocity. And so you have to start thinking about whether or not is there a change in velocity. Now that could be either the magnitude or the direction again, but you need to have seen that change, which means that the initial velocity is different than the final velocity. So there are 5 acceleration formulas that are on our formula sheet. We've already shown one of them, that A is equal to delta V over T, where A is the acceleration, which has units of meters per second squared, which means meters per second, or how many meters per second change do we see each and every single second as the standard units. Delta V, which is a change in velocity, in meters per second, and T, which is time. And again, that delta V and A are both vectors. They have both magnitude and direction. Time does not. Time has standard units in seconds. A second one we've got is D is equal to VF plus VI over 2 multiplied by T. And so we're introducing that VF and VI, which is your velocities, initial and final, meters per second. D is the displacement. And again, that D, VF, and VI are all vectors. T, again, time is not a vector. A couple of others that you will see on your formula sheet. There's 2 that are very, very similar to one another. D is equal to VIT plus 1/2 AT squared. Again, we've got a couple of vectors. And D is equal to VFT minus 1/2 AT squared. And the key difference here really comes down to, are you starting with the initial or final velocity? If you're starting with the initial velocity, you're adding that overall change due to the acceleration. If you're starting with the final velocity, you're subtracting the velocity over time. And one last one, you've got VF squared is equal to VI squared plus 2AD. Now, one of the things you're going to notice with this last formula here is that there are no arrows over things, and that really kind of deals with the squareds because the sign, positive and negative, indicates direction. Well, that squared kind of eliminates that, so this is really just a scalar formula and only gets you magnitudes. You can sometimes figure it out based on the nature of the question. However, it is really a scalar formula. All right, so let's take a look at our first example here. We've got an object that accelerates from an initial velocity of 4 meters per second east. So we've got an initial velocity of 4.00 meters per second east and reaches a final velocity of 8.50 meters per second. And we're going to assume that this is actually in an easterly direction. The question really should have specified that, but we will assume it's in an east direction. And so that's our final velocity over a time of 1.60 seconds. And we want to calculate the acceleration. Okay, well, there's no formula that specifically has these four things. However, these generate what we call the delta V, the change in velocity. That change in velocity is 4.5 meters per second in the east direction overall. So A is equal to delta V over T, or 4.50 meters per second over a time of 1.60 seconds. So when you calculate that out, you wind up with an acceleration of 2.81 meters per second, or per second squared, east as your acceleration. Let's take a look at a second example. Second example we've got here is an object travels uniformly from rest. So we've got an initial velocity of 0 at a rate of 3.15 meters per second squared southeast. So you've got to find an acceleration of 3.15 meters per second squared, and the direction is southeast. How long? Meaning time. So we're looking for time when it reaches a velocity. So we've got a final velocity of 16.7 meters per second southeast. Well, we're using the same formula here. A is equal to delta V over T, and because we started at 0, ended at 16.7, that change in velocity is going to be 16.7. We're looking for time. We've got the acceleration, so you're going to manipulate your formula and then do the calculation of 16.7 meters per second over 3.15 meters per second squared in order to get a time of 5.30 seconds. Let's take a look at a third example. Now, in this third example, a blank ball, really you can put any adjective here. It could be the big ball, or it could be the red ball. Ironically, I'm writing that in orange. Accelerates from rest. So we've got an initial velocity of 0. Down an incline at 1.8 meters per second. That really should say squared there. Okay, finding a couple of mistakes in here. I'll probably have them fixed by the time you're actually watching this video. So we've got an acceleration of 1.8 centimeters per second squared. Now that's not standard units, but as long as we're not mixing our units, we should be fine. And we've got a time of 5.0 seconds. We were trying to find the distance. Well, in this case, initial velocity, acceleration, and time are given, so we're given we can use d is equal to VIT plus 1/2 AT squared, so we're using a different formula. It's the one that corresponds with what we've been given here in our variables list. And fortunately here, there's very little algebra that's needed to be done. VI is 0, T, which is 5.0 plus 1/2 acceleration 1.8 centimeters per second squared, multiplied by the time, which is 5.0 seconds, and that's all squared. Notice in this portion here, the VIT, that comes to 0, and anything added to 0 can be just crossed right out because it doesn't affect anything overall within the equation. And so we're really just saying this, so you're actually just multiplying 1/2, 1.8, and 5 squared. Make sure you do the squared first, but as you calculate that, you get 22.5 on your calculator. The units here are going to be centimeters. Again, reason for that is you got centimeters here, you've got a second squared here, and a seconds that is squared here, leaving you with the centimeters. So it's 22.5 centimeters. So, give this next one a try. Pause the video, try this, and then once you think you've got it, unpause the video, see if you got the answer. Okay, so you should have seen that the change in velocity overall is 8 meters per second east over a time of 5.4 seconds. Using that first formula that we've kind of gone through, you would have wound up with 1.48 meters per second east, or to 2 sig digs, 1.5 meters per second, and again, it's traveling east. We've got one more example that we're going to try here, and there's a couple of little twists with this one. First of all, a car is traveling 15 kilometers per hour east and accelerates to 13 kilometers per hour east. So we see a change. However, we start at 15 and we're going to 13. So in this case, the 15 kilometers per hour is becoming 13 kilometers per hour, and what that indicates is a slowing down. We still call this in physics an acceleration. Now, because it was going east and now going a little bit less east, the change in velocity is actually 2 kilometers per hour in a westerly direction. And so we should see an answer that is negative in the end. The second little twist here we've got is the kilometers per hour. We're going to need to change these into meters per second, mostly because we got our time in seconds, and as we don't want to mix hours and seconds together. So we're going to take this 15 kilometers per hour. Now that's 15 kilometers over 1 hour. And so if you write it like this, it becomes a little bit easier to convert, because 15 kilometers is the same as 15,000 meters. And 1 hour is the same as 3,600 seconds. And as you calculate that out, you get 4.16 repeating meters per second. We can do the same with the final velocity, which is 13,000 meters over 3,600 seconds, and gets you a value of 3.61 repeating meters per second. Okay, we've got a time of 5.4 seconds, which means A is equal to delta V over T. That change in velocity is actually 0.5 repeating meters per second, but it's going in a westerly direction, so we're using a negative there. A is equal to negative 0.5 repeating meters per second over a time of 5.4 seconds gets you an acceleration of negative 0.10 meters per second squared. Now you could put a negative there, or we could write it like this, meters per second squared going west. All right, I've got one more for you to try. So again, pause the video, try this one, and then we'll see how you did and go over it. Okay, your answer you should have wound up with is a negative 2.3 meters per second squared as your acceleration. We had an initial velocity of 12 and a final velocity of 0, which means it's slowing down to a rest. Again, we still call that slowing down or a changing of direction an acceleration, although the colloquial language would have that as a deceleration, but we don't have the word deceleration as a physics term. Over a displacement of 31 meters, we do not know the direction, but we're actually winding up using this scalar value anyway, which you wind up with a negative acceleration, meaning it's going the opposite way in which it was initially moving. If we had this, let's say, as a north, and it would be traveling north, that would indicate south. But if it was traveling east, then the acceleration would have been west, and so on. If it was going to the right, the acceleration is to the left, etc. So if you have any other questions, please let me know, but that wraps up the examples for lesson 1.5.